Alright, so next topic I wanted to talk about is impulse. Um, Impulse is probably the greatest thing since sliced bread when it comes to physics. It's a great little concept. Um, when dealing with systems that are in collision or exploding, we have to deal with this idea. Because when we're talking about impulse, let me rewrite the equation for impulse. Okay? So if you can't see it, this is the change in force, or the summation of the force, times the time it takes for that force to happen, equals the change in momentum. I abbreviate this one right here is this force average. We can say the average force acting on that object times the change in time is equal to the change in momentum. Now, why this thing is so great is that when we talk about things that collide or explode, it's very difficult to talk about all the forces that are acting. Think about a typical car collision. When you're inside of a car collision, you can't really concentrate on all the forces that are acting on that object. You have headlights colliding with headlights, bumpers colliding with bumpers, all sorts of things are going on. So it's nice to talk about average of those forces. So the average force on the car is this over this amount of time. But what makes impulse really, really cool is it can teach you why putting on a seatbelt is a great idea. It can teach you why airbags are such a great invention. It can teach you why stuntmen can fall off tall buildings and survive. In all of those cases, take a car crash. Let's talk about the seatbelt situation. If you take a car and you collide it with another car, okay? You take a car and you collide it with another car. This car here is going to experience the exact same change in momentum regardless, or you will, I should say, experience the exact same change in momentum regardless of whether you're wearing a seatbelt or not. You will be going 50 miles per hour at 1 second, and then after the collision you're going 0. You have the exact same mass in every situation. So this term right here, this change in momentum, this mass times velocity, is going to be the same regardless of whether you're wearing a seatbelt or not. So why is it important to wear a seatbelt? Well, it all is on this side of the equation. If you look at this force times time business, that tells you why you wear a seatbelt. If you wear a seatbelt, you experience this collision as the car experiences the collision. Car collides, crumples, crunch, smash, boom. It all kind of gets intertwined. If you're not wearing the seatbelt, you're sitting in the car, you slam into the steering wheel because you have inertia. You have that tendency to keep moving. Bang into that steering wheel. So you're actually stopping quicker than the car is. Okay? So if you're stopping quicker, this time is small. So if this is constant, whether you're wearing a seatbelt or not, and if you're wearing a seatbelt and experiencing this in a short period of time, that means that your force is large. So this is just some constant. So you can say that your change in momentum is just some constant. Everybody's going to start at one speed. Everybody's going to come to a stop. So that change is still the same. Okay? But with the seatbelt, or without the seatbelt, you experience a very small time, but a very large force. Okay? So here's my time. Here's my force. Okay? So with the seatbelt, or without the seatbelt, your time of collision is very, very short, so you experience a very, very large force. Now, with the seatbelt, you're actually stopping with the car itself, which actually gives you more time. So you get a much larger time, so your force is much smaller. Okay? Taking it one step further now, in cars, you have padding on your steering wheel. It's actually federal law. Your dashboard is padded. Once again, a federal law. Why do we do that? Well, you get a little more time and a little bit less force. Okay? Because you're compressing that padding. You're extending that time. The last trick is the airbag. Airbags are wonderful things because they actually allow you that same constant, but a much larger time to stop. Okay? So that means a very small force. Okay? So no seatbelt, no airbag, very short period of time to stop. Very, very, very large force. Now, as we progressively come up with more and more ideas to lengthen that time of the impact, first by introducing a seatbelt, second by introducing padding inside your car, and then lastly by introducing an airbag. The airbag you still experience this exact same change in momentum. It's just it takes much longer to compress that airbag. So your period of impact is actually longer than the period of impact of the car. Just in the same way that with the padded steering wheel and the padded dashboard. Your period of impact is actually longer than that of the period of impact of the car. So it's kind of this cool little trick that we can do. Now, how does that relate to, let's say, stuntmen? Well, everybody's seen a stuntman jump off a building into a pile of boxes. There's nothing special about those boxes. They're just boxes. Okay? So instead of talking about a car, we talk about this person falling. Now, you have a gentleman jumping off a building into a pile of boxes, or onto a piece of concrete, or in some cases, and if they're really nice, into a pool. Okay? So as they're jumping off, each one of them is going to experience the exact same change in momentum. They're going to go to going really, really fast to stopping. Okay? They're all going to have that same velocity, that same momentum when they hit their object, when they hit the boxes, the concrete, or the pool. You should draw water in that pool, otherwise it's really not going to make much difference between that and the concrete. Okay? But which one would you rather fall into? Well, my list is, depending on the height, pool, boxes, concrete. Okay? And the reason why you don't want to land on the concrete is that you experience that same change in momentum, but you experience it in a very short time, so you have to experience a very large force. Now, I'm stealing notation from Hewitt. I love Hewitt. Okay? So, as we go down the list, you see that boxes coming down. It's the exact same constant, but now it takes longer to compress all those boxes. It takes longer for you to collide and come to the ground. Okay? There's a long period of time in here. This is a big T, where the landing here is a little t, and the landing here actually turns out to be a really big T. Okay? So you can see that you get all these benefits by lengthening your period of collision. And that's all about discussing impulse. Okay? So hitting that water, you're allowing yourself to sink to the very bottom. You have a long period of compression, a long period of collision there. So this T is huge, so that F has to be small. Okay? That's what impulse is. It's a wonderful thing. Boxers, you get socked. Which one would you rather get hit by? Would you rather get hit by a gloved fist, or would you rather get hit by an ungloved fist? Well, I hope you'd rather get hit by a gloved fist. Gloved fists make it survivable. You hit, and that fist compresses over a very short period of time. Okay? Or not a very short period of time, very long period of time compared to just getting socked. Getting socked is a very short period of time. So that's why you wear gloves in boxing. A whole bunch of things are talking about impulse. Okay? There's a whole bunch of real life applications for this. We do it all the time. Cool? Alright, so that's impulse, and that's how it's so important to us. Alright?